Yes, then Professor Sharma advised that you can have this Control E.
No, should I unmute?
Visible, Achi?
Yeah. Next one, please.
Slide is visible, sir?
Yeah, first slide is visible. Can you move to the second slide? I mean,
Yes, sir. Yes.
Let me. Yes. Okay. That's fine.
Thanks.
Fine. No.
I request, sir, will start. I request Bhavani Sinha, sir, to welcome
Oh,
our guest.
am I to start? Or I think Professor Acharya, I think you can initiate the whole thing. I cannot hear Professor Acharya.
Unmute, sir.
Yeah.
Acharya, sir, please unmute. Namaste, namaste, sir. Namaste.
Namaste. Am I audible?
Yes, sir. Now.
And visible also?
Yes, sir.
Good. Very warm welcome to Professor Prasanta Basu and the members of this fellows of INAE and the participants to this 9th distinguished lecture today. And for the sort of brief information, INAE Bhubaneswar chapter organizes this series of lectures along with SOA University and IMMT Bhubaneswar. And this is the 9th lecture in series. Every month, actually, we are now organizing 2 lectures by distinguished personalities from India as well as abroad. And this will continue. For your information, INAE Bhubaneswar chapter is a very small chapter, but we have many associates from the other chapters also. And with this thing, we are trying to do our best. And I'm happy to announce that this year's National Convention of Indian National Academy of Engineering is going to be held here in Bhubaneswar in December. And please block this period, maybe somewhere between 11th to 15th of December. So all of you please try to attend and make it a grand success. So with this actually couple of words, now I will request our Honorable Vice Chancellor, Professor Ashok Mahapatra, who is present here, to tell something about our university. And if Professor Sudarshan Basu, Director of IMMT Bhubaneswar, if it's present here, he will also say something about that. Then I will request Professor Manish Sinha, who happens to be the student of Professor P.K. Basu, Prasanta Basu, to introduce his teacher. And then the floor will be open to Professor Basu. Professor Mahapatra, please.
Good evening, good afternoon, Jai Jagannath. I think it's a wonderful occasion. Professor Acharya is organizing these meetings twice a year. It's the 9th lecture of INAE. And this time we have Professor Basu, is a renowned radio physicist, Professor Misra, Professor Sinha, Professor Nanda, Pro Vice Chancellor of our university, Professor Renu Sharma, and all other participants. It's a very nice occasion. Every time I'm there and meeting a lot more people. There are many familiar faces and many new faces. Regarding our university, it started in 1995 as a trust. Soya Shiksha व Anusandhan Trust. In 96, we started our engineering college, Institute of Engineering Technology and Research. Then it was followed by the IBCS, then nursing college, pharmacy college, and also followed by IMS, Institute of Medical Science, Dental Science, Ministry of Dental Science. Today we have got 10 centers, and this year we are going to have already started on Institute of Veterinary Sciences. We have now started last week the veterinary dispensary, and last week only we had 3 conferences. One was on human value, one was the farmers, agriculture entrepreneurs, and the academia from our university. There are 500 people participated in the exhibition, their products. It was wonderful. Then we had a conference organized by Professor Renu Sharma. Can you hear? Can you hear? Can you hear?
Yes.
Yes, we are able to hear.
Organized by Professor Renu Sharma. It was by the request of AICT that we should have a regional conference on human values. So we had about 70 people from Eastern region. What I'm trying to emphasize that Shiksha Anusandhan had a vision that it should be quality education, skill and innovation, and also socially relevant topics to the region and to the country. In last 25 years of existence of the trust, and from 2007, the creation of university, and 2018, given the graded autonomy, I think we have stood to the test of the time and to the expectation of people of Odisha. During pandemic, when everybody was locked down or shut down at home, in phase 1, we have more than 2,400 beds. And in phase 2, we escalated those beds to 2,660 beds with 250 ICU beds in about 6 locations and 5 different districts. So we treated more than maybe 50,000 patients, and people like governor, the governor, many ministers, senior IS officers, and they all were coming to our hospital. Our hospital is probably getting about 5,000 patients a day. India, from Odisha, from part of the West Bengal, which is neighboring the part of Odisha, from Chhattisgarh, and also Telangana. So it has become a education and service-oriented hub. Our medical college gives very good care with a very low cost. Now recently there is some ultimate with a corporate hospital with all 5-star facilities. So over the years, the Soya Trust has the university, the newspaper, which is daily newspaper Pramaya, and then News 7 channel, which is for the TV, and Soma Real Media, which also undertake movies, socially related movies. Now we have a corporate hospital, and that all shows that the vision of giving a quality education, socially related context of cultural, social, and health sciences. We have developed a Prachin, which is preservation or restoration of Indian ancient tradition. We have IKS, Indian Knowledge System. We have NCC. We have 1,800 people of our university are enrolled in the NSS, and about 200 coordinators. We have adopted 25 villages. Our students go to villages and teach them Swachha Bharata, good nutrition, how to lead a healthy life. During pandemic, more than 20,000 food packets were distributed to the immigrant labor coming through the highway, this is the highway which is from Howrah to Calcutta to Chennai. So I think the university has done well. It is the people to judge what we have done. Coming back to engineering and Dr. Basu and Dr. Sinha and all this, we are working on biodiesel, nanotechnology, and many advanced technology in science and technology. In molecular medicine side, we developed that lab for the BLS3 lab for the testing the COVID test. We started doing fast liver transplant in our hospital. We have done more than 13 bone marrow transplant in last 3 years. It's the only center in Odisha which is doing bone marrow transplant. And recently we have a NAC visit. They are very happy seeing the hospital and our research and innovation facility. They talk to the students, the family, parents, the foreign student, the patient relatives, and other people they met in the hospital, and they were thinking that it's quite good. So it is made an impact in Odisha and in India. Now we rank in 2021, 20th university in the country and 20th ranking in medical science, 32 ranking in engineering science, 14th ranking in dental science. We are also trying to see ranking in management school and also agriculture and law. So I think it is slowly and steadily making a progress both in education, in research and technology innovation, and socially related context like we have a weather prediction center which is connected to 30 districts of Odisha, and they give a very quick every 2-hourly update. Like yesterday we had rain, they were predicted which district will have rain at what time and what should be average speed of the wind flow. Every 2-hourly our weather prediction center send to all districts the signal what type of weather they are going to face in next 2 to 4 hours time. I think these are small, maybe sound small thing, but socially and really practically relevant to our day-to-day affairs. So I think I thank Dr. Acharya once again. I think he is always in his toes to make others work and get the best people to deliver lecture to motivate our teachers and students. So whatever I praise to Dr. Acharya will be small for him. Of course, he is one of the gems of our states, being the chairman of AICT. So thank you, sir, for organizing such lectures. How much our student benefit will the time will tell. We never know who is learning what. Learning is not a forceful event. It must be a self-interest learning rather than forcing somebody. I think over the years people will be interested. It will be very, very useful to time to come. Thank you very much, sir.
Professor Basu, are you present here? Professor Basu?
I mean, Professor Suddha Sattva Basu, not Professor P.K. Basu. Professor Basu.
Professor Suddha Sattva Basu. Now, possibly he is out of this place. He was in Hyderabad a few days back. Maybe he is there. Now I will request our Professor Bhavani Sinha to introduce his teacher, Professor Prasanta Basu.
Well, all the distinguished fellow members of INE BB Bhubaneswar chapter and all the distinguished participants, it is my proud privilege to introduce today's speaker, Professor Prasanta Kumar Basu, for this 9th lecture in the distinguished lecture series of INE Bhubaneswar chapter. Professor Basu, in fact, as already mentioned by Professor Acharya, that Professor Basu was my teacher, and he received his all degrees, BTech, MTech, and PhD from the Institute of Radio Physics and Electronics of University of Calcutta, where I also studied. He joined this University of Calcutta at sometimes in mid-60s, and I was his student in early 70s, okay, sometime during that time. Professor Basu retired from the Institute of Radio Physics and Electronics in 2011, and after his superannuation, he worked as the UGC BSR, the Basic Scientific Research Faculty Fellow. He was also a visiting professor at IIT KG Kharagpur and also National Chung Cheng University of Taiwan. And after that, he was also engaged as an investigator on an Indo-Taiwan project. Professor Basu was also an Alexander von Humboldt Fellow of Germany. He was even the first INSA Research Fellow, and he was a visiting professor in TIFR while he was the faculty member of Radio Physics and Electronics Department in Calcutta University. He was a visiting professor in TIFR, a visiting professor in McMaster University of Canada, and visiting professor of National Chung Cheng University of Taiwan, and also the INSA Royal Society Exchange Professor in UK. He also served for 8 years as a member of EPSRC College, UK, to review their projects. He was an excellent teacher, has always been adjudged by his students, including myself. And he has a very, excellent research record with about 140 high-quality journal papers, 4 books, and 2 book chapters in his area. He is an authority in the area of solid-state physics and devices. He has guided a large number of PhD students, and still he has been guiding some students, I believe. In fact, he initiated the first the International Conference on Computers and Devices for Communication, CODEC, this CODEC series that was actually initiated by Professor Basu. And this is this computing and communication. So today's, if you see today's scenario, so there has been a perfect marriage between these two disciplines. And that has led to such a wonderful development worldwide in having the smart world all throughout, both this communication and computing. With this, CODEC series also, he was, he has been able to invite a large number of international scientists to this conference, and it has been really successful one. He also was instrumental in earning the title of UGC Networking Resource Center in Physical Sciences for the Institute of Radio Physics and Electronics. In fact, this institute was the first in India to earn this title from the UGC. He has been very successful in making an inter-institutional research collaboration with the faculty members from Radio Physics and Electronics, Institute of Radio Physics and Electronics, NIT Delhi, McMaster University, and National Chung Cheng University of Taiwan. And he has also been engaged in some collaborative research projects with all of them and writing books in his area. So today we are very fortunate to have Professor Basu here for this distinguished lecture of the INE Bhubaneswar chapter, and he will talk on silicon photonic systems as interconnects in current data centers, which is one of the very appropriate topics considering the present day scenario. As I told, that's a marriage between this computer science and communication. So this is one of the very relevant topics, and it will be definitely, we will have many illuminating ideas in this area from Professor Basu. I would cordially invite and request Professor Basu to kindly continue with his lecture. Thank you very much.
So may we request Professor Basu?
Well, thank you very much. First of all, I must thank Bhavani for giving this very nice introduction. And can you, Professor Sharma, can you share the slides? Is it?
Yes, it is visible.
Oh, is it visible?
Yes.
Yes, yes.
Is it moving? Is it
I
moving?
can see it. Yeah.
Silicon
see.
photonic system.
Is it moving?
No, it's not yet moving, just stationary.
I suggest just slideshow. Slideshow.
No, I think Professor Sharma can help you in going to the
Is
next
it
slide.
moving? Can you see?
Yes.
Yes,
Is
yes,
it moving?
we can see.
Okay.
Absolutely fine.
So, a very good afternoon. The title has already been stated: Silicon Photonic Systems as Interconnects in Current Data Centers. And first of all, I would like to thank the organizers, that is Professor Damodar Acharya, President of INAE Bhubaneswar, also SOA, Professor Bhavani Sinha, both INAE and SOA, university staff of SOA University, IMMT Bhubaneswar. And I would like to acknowledge my collaborators, that is Dr. Brotodip Mukhopadhyay from Reddy Physics, Dr. Rik Mantra Basu from EC NIT Delhi, Professor Guowen Chang from NCCU Taiwan, Professor Nikhil Ranjan Das from Institute of Reddy Physics and Electronics, Calcutta University, and Professor Jamaluddin McMaster University, Canada. So I would say, is it visible? Is moving?
Yes, this is moving, please.
Okay,
Yes.
fine.
Yes.
So it's supposed to be a distinguished lecture, but I would say that I am not an expert in silicon photonics interconnect. So this talk will be just a report by a journalist in a science magazine, nothing more than that. So maybe a kind of tutorial, or I mean, it's not an expert lecture. How do I venture to give this lecture? Because it's based on my knowledge in writing these books, which are shown. And in particular, we are planning to write a revised edition of this book, Silicon Photonics. And the reviewer suggested that you should include the topics in more detail in the revised edition, that is this interconnect and data centers, etc. And also, we did some research on silicon or group for photonic devices, but it's usually on active devices like lasers, photodetectors, modulators, etc. I'll come to these things a little bit later. So let me tell you the objective. It's basically a communication system, and it's a basic communication system using fiber optics. And to start with, I shall introduce the basics of fiber optic communication systems used in long haul networks. And one example is given in this right hand side. You see, it's India, and it's connected to different countries through undersea fiber optical networks. You can easily see that there are a large number of fiber optic networks. How do these networks operate? So after giving a very tutorial introduction of this topic, I'll enter into the main subject, that is the problems of interconnect in very large scale integrated circuits and how it affects the performance of data centers. Then I will introduce silicon photonics, why that is needed. And also in connection with this fiber optic communication system or silicon photonics, I will let you know the devices and components which are used in silicon-based photonic integrated circuits. That's needed. And then I'll scale down and I will introduce the optical communication system for short distance application. This picture shows that these two devices are connected by a waveguide system. I will narrate this. So this may be a chip, and the other end is another chip, and these are interconnected. One example. And state-of-the-art technology in modern interconnects. And finally, I will mention some of the drawbacks and what is expected, what is going on, what kind of research is going on to mitigate that problems. So let me start with basic of optical communication. Well, I start with a very simple block diagram of a communication system. Anybody having higher secondary knowledge in higher secondary physics or undergraduate training in electronics and communication and all other branches are familiar with that. Is communication, that is information is transmitted from one end to the other end. I take a very simple example of telephony. What is that? In telephony, I speak and my voice is in a second mechanical vibration. So it's converted to electrical form by a transducer known as the microphone. And usually in communication systems, this is analog signal, which is continuous, it's digitized, and this digital information is fed to the information in electrical form is fed to the transmitter system, and transmitter system may be different. In your mobile, it may be a microwave source with antenna. In your optical fiber communication, it will be something different. In radio communication, it will be something different. So information in this figure, what I mean by information in electrical form is your voice, which you want to convey to your parents or to your friends at the other end. So this modulator and information is, so to speak, modulates the carrier frequency generated in the transmitter. Then this modulated signal is fed to the channel. Of course, there is some additional noise. Forget about that. And after traversing a large distance, it's received by the receiver. So it's a weak digital signal, and you have to amplify this weak signal. You have to process this. You have to make it in a perfect, perfect decipherable form. And that digital signal should be converted to corresponding analog electrical signal, and then it's fed to the loudspeaker, and you hear the voice of your friend, or your friend listens or hears the voice you have transmitted from the end of the communication system, and for example, a telephonic system. So that's the basic principle used in every communication systems, of course, with some changes because of the form of transistor, transducer, or transmitter, or receiver, and the communication medium. I will come to that. So let me illustrate this by using an example, simple arithmetical example of a voice signal which is digitized. So it's an audio signal, you know, from higher secondary. It covers up to 20 kilohertz. But in most of the situation, if you cut it to 4 kilohertz, you will be able to distinguish whether Lata Mangeshkar is singing or whether Kishore Kumar is singing. You can make a clear distinction. So that's fine. And there is a criterion which is called a Nyquist criterion. If you sample this 4 kilohertz continuous signal at the rate of twice the highest frequency, so in that case, twice the highest frequency will be 4 kilohertz into 2, that is 8 kilohertz. And that sample is each amplitude is sampled at the rate of 8 kilohertz. That means 8 into 10 to the 3 times per second, and it's digitized to 8 bits. So what is the total bit rate for a person when wanting to make a conversation through telephone? It's 8 into 8 into 10 to the 3, that is 64 kilobit per second. For a single subscriber, you need 64 kilobit per second. If you have 32 subscribers, then the total bit rate will be 32 multiplied by this 64 kilobit, and that is nearly 2 megabit per second. This several 2 megabit per seconds are interleaved, that is placed side by side, and this hierarchy covers larger bit rate. And in optical communication system, this 2.5 gigabit per second, 10 gigabit per second, 4 times higher, 40 gigabits per second. You can increase to 160 gigabit per second, but that makes things very complicated. So it's fine. So what do we learn from this? We learn that if you have 40 gigabit per second, and for each subscriber you have 8 kilobit, 64 kilobit per second. So 40 gigabit by 64 kilobits per second. A simple arithmetic will say that how many subscribers this service providers can satisfy at a time. So the more is the bit rate, the more you can satisfy your subscribers. So that's the principle. And if you go to higher frequency, that is optical frequency, from radio frequency to microwave, microwave to terahertz waves, terahertz waves to optical frequency, which is quite large, you can accommodate a large number of signals or large number of information, and you can satisfy a large number of subscribers. So if you install, you get your money and you can earn a large profit by that. So with that, I describe is the electrical pulses, which is digitized from your voice signal. It's fed to a transmitter, which contains a laser, light amplification by stimulated emission of radiation. Then those pulses, optical pulses, traverse through a section of optical fiber. It gets attenuated and distorted, and it's cleaned by using a system known as optical repeater, moves another section of the fiber, moves again, and finally is received by the receiving system. That is, receiving system is a friend, this is the telephone of your friend in, say, England, and he receives that, he gets that signal, it's processed, and it gets back in digital electrical form, and it's fed to it's converted to analog signal, fed to a loudspeaker, and he listens to your voice. So with that, let me just give you some idea about the components which are used. Naturally, as said, we are interested in long distance communication. Also for short distance communication, the transmitter which is needed is called a laser. What kind of laser? There are many different forms of lasers, but we are using, and in fact, everybody use this semiconductor laser. Why semiconductor laser? Because that is very simple, and it can be batch fabricated. It's very cheap, and it fits into the core of the optical fiber, which is your medium. And you know, there are three different processes. One is known as absorption, shows in the top. A photon is incident. It lifts an electron from the lower state to the upper state. It goes that goes there. The right hand side indicates the final state. This process is known as absorption. There is an opposite process which is known as spontaneous emission. An electron is the upper state. It jumps down spontaneously, and the excess energy is given in terms of a photon. And there is an additional phenomena which was discovered by Einstein in 1917, that is called stimulated emission. The same thing, you have an electron in the upper state. Now you have a inducing photon. If you allow this photon to impinge on your system, it will induce the transition from the upper state to the lower state. And what is the result? You get one photon at the input, and you get as a consequence, you get another photon, so two photons. So naturally, you see that if you can somehow augment stimulated emission process, in the input you have one photon, in the output you have two photons. So naturally, there will be amplification of light waves. And so the problem or the task is to create a suitable condition to make stimulated emission dominant, and that process is known as population inversion. You have more electrons and more particles in the upper state than in the lower state, which is some kind of non-equilibrium situation. But it's a lesson from electronics or basic electronics that if you have an amplifier, in order to convert this to a self-sustained oscillator, you have to provide some kind of feedback, and that feedback is provided by two plane parallel mirrors. So by using positive feedback in right phase, and you can convert this amplifier into a self-sustaining oscillator. And so you have a loser instead of a laser. Light amplifier, amplification by stimulated emission of radiation is not that. You have light oscillation due to stimulated emission of radiation. So why loser? If you submit a project which carries a negative sense, you won't get any funding from any agency. So that's why they're stuck to the name laser. So this is a principle. But in semiconductor laser, this is the basic principle. It taught in all elementary textbooks. But in semiconductor laser, you have something different. You have a PN junction, and this PN junction you forward bias. And if you forward bias this, you have enough electrons injected from inside to p-side and enough holes, that is a empty states, injected from the left hand side to right hand side, and the middle region, which is called the active region, you have the electrons in the upper state, that is upper band, conduction band, and you have empty states in the lower band, that is the valence band. And so you create a condition for population inversion, and naturally you get stimulated emission dominating over the lossy spontaneous emission process. So that's the basic principle. Well, when you talk about structures, there are different structures which are called double heterojunction, quantum well, quantum dot, etc. But usually in the connecting systems, interconnects, you have a special structure which is known as the vertical cavity surface emitting laser. This is a schematic of VCSEL, and you are all familiar with VCSEL because the vertical cavity surface emitting lasers are used in optical modes in computers. So you see, just put it upside down, you will find some red light is being emitted, and that is VCSEL. And if you consider the importance of any area by the number of Nobel Prizes, there are many Nobel Prize winners: Towns, Basov, and Prokhorov for measure and laser, Arthur Shallow for optical measure, Herbert Kromer and Zores Alfarov for double heterojunction, and Charles Cow for optical fiber communication. So that's all. Well, I have talked about transmitter, and on that transmitter you impress the signal, digital signal you derive from your voice or from your computer or from your the picture. I'll come to that block diagram a little bit later. And on the other side, that is the receiver side, you have to convert the optical signal into electrical signal. How do you do that? Again, you use a PN junction, use it in the reverse bias. So light impinges, it creates electrons and holes, and there is intrinsic electric field in the intrinsic region. It separates electrons and holes. They move through the external circuits, create a current. So light converted to current. That's the principle of photodetectors. There are different kinds. I don't want to enter into the details. So if you consider the characteristic of a laser, you will find that this is the current, forward bias current. Initially, you do not get a copious emission, but as soon as the current increases the threshold, there is a large increase in the optical output. So the principle of modulation, that is you have to impress your voice signal or data on this, and the principle is illustrated here. You use a bias, a DC bias, impress your electrical signal, and from these characteristics you find that this electrical signal will be converted into a corresponding optical signal. You can use a digital signal in this way. It will be converted into corresponding digital optical signal, but there are some distortions. Oh, I don't want to enter into those things. And this is a simple direct modulation. If you want to move further, that is, if you want to make the system more attractive, then you have to use external modulators. So I come to the next thing, that is this is the basic principle. What do you do? Instead, I have illustrated this by using a single transmitter and a propagating medium and a receiver. This transmitter is your telephone, and this receiver is your friend's telephone at UK. So you just use a number of transmitters, and thereby you use those digitized signals, and many more digital signals derived from many more subscribers. You combine them and send the combined signal through a section of the optical fiber, In the other side, you just separate this. This process is known as demultiplexer, and demultiplexer is fed to different receiving systems, and you have different subscribers connected to different subscribers at the other end. So data rate is increased n-fold, that is number of transmitter is n. So let me take a very simple example. Each transmitter carries a data at 40 gigabit per second, and let the number of transmitters be 100. So just multiply this, you will find total information transmitter rate is 4 terabit, that is 10 to the 12 bits per second, and you can satisfy many subscribers. Again, that is illustrated. You have your computer here. I omit different things. Your home computer is connected to some kind of cable to a mobile system, and then it goes to substation, central station. Then it goes to the central station of your local optical fiber network. It modulates, then multiplies, then it goes via a section of the fiber. It faces different repeaters, and finally it's demultiplexed and detected, separated, and finally you get your detected signal and goes to the computer of your friend in Russia, and so you send an email, and your friend receives that email in the original form as you have transmitted by using this fiber network. So this is the story basic of optical fiber communication, and that principle is translated into the short distance communication. Now we come to the system why silicon photonics. And you see that this is a wafer, silicon wafer, which is used in VLSI in making integrated circuit chips. Why silicon? That is the best material, and you can grow different insulators and all that. And this is a cross section or a view of a 12-inch diameter wafer, and by the same processing steps you can fabricate a large number, an array of dies, and one die is illustrated by this orange color. So you can easily realize by using the same processing state you can get a large number of identical ICs which you can use. And that's the beauty of silicon integrated circuits. That is, it makes the IC chips so cost effective, and you can use this in your desktop, in your mobile, and everywhere, and you get at reasonable prices. So that's the beauty. Integrated circuits, electronic integrated circuits. This is a map how integrated circuits are moving, and the basic building block in an integrated circuit is a field effect transistor, metal oxide semiconductor field effect transistor, a combination of N-type and P-type. Forget that. And the size of each transistor is 5 nanometer, 5 into 10 to the minus 9 centimeter, and it's moving faster. But remember one thing, if you have a 5 nanometer transistor, it should be connected to large number of similar electronic devices, silicon-based electronic devices, and there should be a connector connecting one device to another device. And what are these connectors? Usually copper or aluminum. As you reduce the size of your transistor, you can send your signal from one end to other end very quickly, because you reduce the length, and the length reduction increases the delay, that is called the delay, time taken for transmission of a signal from one end to other end. But the price you have to pay, there is a copper interconnect or aluminum interconnect. As you reduce the size of your transistor, your interconnect should be reduced in length, in cross section, and everything, and it behaves as a RLC circuit, that is resistance, the inductance and capacitance, and that is very nasty. It increases the delay due to interconnect. And also in present day VLSI, you don't have a single layer of interconnect. There are 1, 2, 3, 4, 5, 6, 7 layers of interconnect. And these interconnects are metallic interconnects. And you should be careful that each layer should not make a cross with the other layer. And so you have to avoid short circuit, and you have to introduce an insulator in between these interconnect layers. Oh, that is problematic. So what is the solution? The solution is inevitable. If you replace the electrical interconnect by optical interconnect, then you learn a lot of things. So now we come to the promise of silicon photonics. It's quoted from Physics World, a science magazine, 2019. Google in 2009 predicted that calculated that a single internet search consumes 1 kilojoule of energy. And industry experts expected that in 2016, world data centers, massive monoliths of servers and switches, data centers that is your Google, Facebook, and all such things, Twitter, all other things, they will consume, they are consuming almost 40% more electricity than the entire UK. And there are problems because new devices are coming, consumer devices, high definition television is coming, and artificial intelligence is also coming, and telemedicine and everything. So the demand for data rates is also increasing, and you have to handle all those things. And there were predictions in 2020, 2000 and 2009 is from Stanford. He predicted that this capacitance is responsible for this, and so it's more serious at the data center level, and the power consumption will be enormously large. So that brings photonics instead of electronics in interconnect. What are the advantages and disadvantages? Electronics have speed limit, as I have mentioned. Photonics does not have speed limit. Speed of light divided by the material's refractive index, maybe 2 into 10 to the power 8 meter per second. That's quite large. Metallic layers need insulators in between. Light beams can cross without interference. That is the advantage. Electronics, too much power dissipation, and in photonics, less power dissipation. This advantage is green. Size is too low, less than 10 nanometer in present day mobile systems by Intel and all other companies. They are using 10 nanometer nodes. But in photonics, I will come to this, the size is too large, is of the order of wavelength divided by refractive index is 200 nanometer. So 10 nanometer, 200 nanometer, compare this. And monolithic integration in silicon is possible in electronics. Unfortunately, in photonics, that is not possible. So now I introduce why we should use interconnect, optical interconnect in place of electrical interconnect, and what should be the platform. This naturally silicon, because all electronic circuits are grown on silicon. All the companies like Intel, then Global Foundries, IBM, TSMC, they have built up their wealth, that is foundry system, by using silicon and the corresponding things. So if you have these silicon photonics chips, you must use silicon as your platform and use the same fabrication facilities to get your interconnects and all that. So here is an illustration. A CPU is connected to another CPU, and this is a CPU is connected to electrical transmit and receiver. Then use transmission lines, maybe optical fiber, maybe metallic wires. It goes to the other side. There is electrical transceiver, and it connects to CPU. Different electrodes to the different electrodes in the other CPU. And the link distance is severely limited as the bandwidth it increases, as I mentioned in the earlier slide. On the other hand, is optical interconnect. Instead of transmission lines, that is metallic transmission lines, you can use optical fibers, or you can use optical waveguides, and the same thing. And it's illustrated here. One CPU is connected to a transmitter and receiver, because you have to transmit and you have to receive signals from the other CPU. And there is, in this system, you have a light source, that is laser, then optical modulator, and all other components which I have mentioned in connections with optical fiber. Let's skip that. Now come to the activities. First is lightweight communication in computers and fibers, and the next come this between the cards, different cards within a desktop or a laptop, and then it comes fiber to the home, and finally replacing copper interconnects in VLSI. What are the players? Players are too many: Intel, IBM, HP, Kotura, Sun Microsystems, IMEC Belgium. It's a non-profit organization. ST Microelectronics, Alcatel-Thales, Nippon, Hitachi, and Singapore's A-Star. And there are recent new companies starting from startups, Luxtera, and of course service providers like Facebook, Google, Cisco. They are interested in this business and these activities. There are many different projects funded by government. There's DARPA, multi-university research. There is MURI. In Japan, there is MORAI, optical interconnects. In UK Silicon Photonics. European Union, Helios, 19 universities. Platon, well, this BOOM surface is collaborative effort between Germany and Italy. And IEEE Photonics Society holds annually Group 4 Photonics Conference. And this field is not yet mature. So I think I can emphasize the importance of this of silicon photonics as the interconnect. Now the question is, why silicon? Why not other material, indium phosphide? Well, in fact, optical fiber communication systems, they use lasers and all other devices like photodetectors, modulators, etc., by using another material, which is a 3,5 compound material, indium phosphide. But we prefer silicon instead of indium phosphide because of these following reasons. Red is a drawback and green is advantage. Indium phosphide is expensive material, silicon is cheap material. Well, cheap material in the sense that in these processing steps has been optimized to make it as cheap as possible. Medium yield and high yield, small footprint, high index contrast in 1D. Small footprint is needed because you have to grow integrated circuits with a very tiny footprint. But in silicon, it's extremely for the small footprint so far as electronic devices are concerned. You can grow a native laser, but unfortunately, you cannot grow any laser by using silicon or germanium or any other material. That's the drawback. Poor native oxide, forget about that. These are these things. And is a small wafer, 75 millimeter. Maximum for silicon, it's 300 millimeter, that is 12-inch diameter. It's brittle material, it's a strong material, and there are some other advantages and disadvantages. So main disadvantage is that if you use indium phosphide, you have to spend a lot. Otherwise, you can, if you can use accepting that laser, then you can grow everything very cheaply, and you can sell it to your vendors, to your subscribers, and all those service providers and all other agencies which are interested in that. And then next thing is I told about metallic conductor. And in long distance communication, there is a kind of waveguide, optical waveguide. Optical fiber is a kind of waveguide. It's a cylindrical waveguide. But when you have the planar technology, that is chip to chip interconnect or CPU to CPU interconnect, these connectors should be of planar form. It should be a planar waveguide. Waveguide means light is confined within the core of the material. The principle is simple. It's again has secondary physics. You shine light, and this is two different materials. The top one is lower index, and the lower one is higher index. So this Snell's law. If you shine light with the angle of incidence exceeding the critical angle, then you get total internal reflection. So you shine light, it's reflected at the higher index material core and lower index material cladding at the interface. It gets reflected and moves in a zigzag way that is shown in all these diagrams. So if you launch light at the left hand end, this it propagates in a zigzag fashion, and received this light is received at the other end, that is right hand side. So you can guide light and you can send information by using this light. This is a very simple principle, but it can be extended by using the Maxwell's equation and all those things. So I don't want to enter into those things. These are different forms of silicon-based waveguides. It can be grown by using silicon. So everything can be done with silicon, and some Indian institutes, some examples are given here. The different passive devices using waveguides for the communication link. And you can see Sumit Rai from IIT Kharagpur, Vijay Das from IIT Madras, Mukesh Kumar from IIT Indore, Vijay Kumar from IIT Roorkee, Sumanta Gupta from IIT Patna, Ramesh Sonkar from IIT Guwahati. And they all participated in our international workshop on Group 4 Photonics, organized by NIT Delhi and NCCU Taiwan. It happened during March 17 to 23. We invited a few more people, but they didn't respond. So forget about that. I give you some idea the kind of activities going on in educational institution. So here are some examples of the chips which are used in present day data centers and network. Let me illustrate this with the chip which was developed by Intel. As I have mentioned, that wavelength division multiplexing, by using wavelength division multiplexing, you can increase the data transmission capacity. So you have 4 transmitters using 4 lasers. These are hybrid lasers. Why hybrid lasers? These lasers are grown on indium phosphide, not on silicon, because you don't get laser action in silicon. So you just make a kind of bonding and use that laser. And then you have 4 modulators. For 4 modulators, each modulators, you send data at 12.5 gigabit per second per channel. So 4 into 12.5 is 50 gigabit per second. Then you have a multiplexer, and that multiplex signal is fed to a waveguide, that is optical fiber, and you get 40 gigabit per second. It goes to the other end. In the other end, you have the similar receiving and demultiplexing circuit. So your connection, that's the optical interconnect, that is accomplished. Here are some more examples. I don't want to enter into these details. Again, this wavelength division multiplexing, I have mentioned, these different colors indicate that different wavelength lasers are used. Then different modulators, you impress your digital signal on each of the modulator. Then you use a multiplexer. Then you have a system of interconnects, goes to the other side, demultiplexed. Then we have a set of photodetectors. It converts the optical signal into electrical signal. Then you use CMOS circuit to process that. And finally, you feed that signal to your television to decipher the signal sent by me, which is to be received by my friend at UK, or the telephone signal I am sending to be received by my parents in the United States, or the email I have sent from my end to my friend in, say, in some other country like Germany. I don't want to enter into details of these processes because that won't be interesting. Here are some examples how these chips are made. Here is an example of 8-inch silicon on insulator wafer with various photonic components. It's perhaps by Luxtera. I forgot to include that. This is a photograph of SOI, that is silicon on insulator photonic chip, fabricated at Institute of Material Engineering, A*STAR, a non-profit organization in Singapore. And this slide indicates that some view graph of the modulator and silicon photonic system, planar systems. It's called a ring resonator modulator, and the lasers are 3,5 compounds and alloy layers are grown or bonded onto SOI silicon platform, and SOI silicon platform can be grown by the standard CMOS technology. So here is a summary, that is how this interconnect evolved from public city to city, that was the optical fiber. Then optical fiber interconnects made a progress from metro building to building. And then we come to the actual silicon photonics area, that is datacom, from one rack to another rack using fibers and this silicon photonics technology. Then computing within a rack from one board to another board, connection is made. I mean, a quick connection is made by using this optical fiber and transceiver system. And finally, you have to have this chip to chip interconnect. Is again I have illustrated with the aid of a diagram. And the last stage should be a MOS device is connected to another MOS device within a chip by using the silicon photonics technology, and that's really challenging. Forget about this. These are different schemes that repeats the same principle, so there is no need. Now, what next? Now, I have talked about this integration. That is, you have to integrate everything, that is your electronic processing using silicon as the platform, silicon IC chips, and you have to integrate this with silicon photonics chip. Of course, forget about the laser, which is a limitation. That is a kind of heterogeneous integration. You cannot achieve everything integrated on a silicon, that is silicon. Fortunately, there is some ray of hope. A layer, an alloy, germanium and tin, it can be grown on silicon platform to make a laser. Some work is going on. We are also involved in some design issues and modeling issues, but there is a size mismatch. What is the size mismatch? As I have mentioned, that electronic chips say 10 nanometer, and 10 nanometer is the device size, the ultimate device size. And what should be the actual footprint? Maybe 5 millimeter by 3 millimeter die, including billions of transistors and everything. But if you want to integrate this with a silicon photonics chip, then size is enormous. The size is, as I have mentioned, is a fundamental law of physics, which is called the fundamental law of diffraction. You cannot focus or you cannot concentrate light no better than wavelength by refractive index. So if you have 400 nanometer as your light, wavelength of light, and if your refractive index is 2, so 400 nanometer by 200 nanometer. Compare this to 10 nanometer, 200 nanometer, enormous size mismatch. So is difficulty in achieving electronics photonics integration. That is one problem. And speed limit due to inherent modulation bandwidth of lasers is usually 60 gigabit per second. and it can be increased at the cost of wavelength division multiplexing. You have to use a lot of lasers, number of lasers, you increase the cost. And the current and future demand for bandwidth, not only in data centers and high performance computers, but also in networking like 5G, 6G mobile. So it's, you have to handle a large amount of bandwidth, large bandwidth in order to satisfy your bandwidth hungry subscribers. And more demand is likely with the spread of artificial intelligence, and you have to limit the power consumption to a very low level, and this requirement is 10 picojoule. Picojoule is 10 to the minus 15 joule per bit at peta, that is 10 to the 15, or exa, that is 10 to the 18 flop rates. Oh, this is very difficult and size mismatch. So what is is the current research is you move from electronics and then to photonics. Now you go to plasmonics, and plasmonics is a just is a propagation and transmission and processing of plasma waves called the surface plasmon waves in a metal semiconductor or metal insulator interface at the surface of metal semiconductor interface, that is plasmonics. And this diagram you can easily identify that for electronics this size is no problem, but your bandwidth is limited to 1 gigahertz. When you come to photonics, size, I mean bandwidth can be extended to a very high level, but the size is limited, as I have said in the earlier example slide, that is maybe 200 nanometer. But if you can use plasmonics, you can go to sub-wavelength region, and you can reduce the plasmonic circuits to a level which is almost comparable to electronic things, and that's the solution. So it's an example of using germanium photodetector, silicon dioxide on insulator. This is a laser, vertical cavity surface emitting laser using germanium tin. It's grown on bulk silicon as a substrate compatible with that. Not only that, I have finished. Not only that, there are many other areas covered by Group 4 Photonics. It's very difficult. I have covered only for communication and all other things. There will be optoelectronic integrated circuits, these components, laser, LEDs, wave guiding, different physical phenomena, how these are grown. I have given you a diagram of molecular beam epitaxy, which is used in our University Center for Research in Nanoscience and Nanotechnology, and different junctions, then different materials, and futuristic applications of quantum computing, quantum information processing, and encryption, and other processing systems is plasmonics, integration, metamaterials, spintronics, and there are many different application areas, that is free space, mobile, satellite, terahertz, healthcare, beam steering, automotive cars, artificial intelligence, and energy harvesting. So I have finished, and thank you very much for your patient hearing. I'll be glad if you ask questions. I'll try to give answer to your questions if possible. Thank you very much.
Professor,
Anything?
can
I
you
think,
hear me?
Sorry?
Professor Sharma, are you present? Please, any questions? I think you are mute.
No, sir, I'm not mute. I'm not finding any raise hand in the group.
Okay. Is there anything in the chat box?
In fact, this is
No,
a heterogeneous audience. I mean,
Yes,
coming
yes.
from different disciplines, and I
Then
have tried my best.
that is okay. I can understand. And Professor Nanda, are you present?
sir is there, sir.
Yes, sir. Yes. Sir.
So I think it was an excellent lecture, Professor Basu. There
Thank
were
you.
many stalwarts from the Institute of Radio Physics, and you were definitely one of them. And we had
Thank you very much.
Professor Sanyal, we had Professor Chakrabarti, then our Professor
Diana, okay, A.K. Chaudhary.
so many of them, including Professor Datta Rai from IIT Delhi.
Yes.
And today, actually, we had the pleasure of actually listening to you. And for a layman, for a Hathoda engineer like me, who doesn't understand even ABC of electronics and communication, many things were amply clear to me from your excellent lecture.
Thank you
Now,
very much.
Professor Nanda, please propose a. Please summarize. You are a man from electronics side. You are much better off, so you can summarize and also propose a vote of thanks.
Thank you, sir. Thank you, sir. Good evening, everybody. I think it was a very illuminating and very befitting lecture. Today's demand is communication, and the bandwidth is the issue. And as Professor Basu, who is a stalwart in this field, he could identify the long-haul communications to the chip-to-chip communications, like we are interested, like in AI, machine learning, and high-speed networking, 5G, 6G. I think we are entering into a new paradigm, and our next generation has a new future. They need this kind of bandwidth, and already we are facing. The more we grow, we're facing more shortages. I think rightly Professor Basu has suggested the demand and the technological bottleneck of the devices. I think there is a synergy between photonics and silicon. I think VLSI and plasmonics. I think this synergy will definitely provide some solutions to our new demand, and this will be ubiquitous in every part of the society. Therefore, device and communication between computers, between CPU, and between the long haul communications, we need optical fiber. And the new paradigm we are entering is a quantum computing. I believe the computer science will have a radical change, paradigm shift, once quantum computing comes into place and will be visible everywhere. Therefore, I believe to face those challenges, this kind of technology will be the right approach and right time and the contemporary solution for the current issues in the globally as well as locally. So the basics were very well illustrated by Professor Basu, who is very famous teacher. I also know, and he is very has studied in depth and lucidly presented very simply for a common man to understand the problem and the solutions right from the beginning of the basics of transistor. So thank you very much, sir. Thank you very much for your illuminating speech, lucid presentation, and definitely it will be, you are one of the best teachers at radio physics. So we expect that the presentation will be quite lucid. So on behalf of INE Bhubaneswar chapter and Shiksha Anusandhan, Jimtubee University and IMMT, I extend my heartfelt thanks and also the personal thanks to Professor Basu, who could spare his time at this age and could explain from the basics to the current contemporary research. So thank you, sir, for spending your time with all of us, illuminating to the new challenges and also to the heterogeneous mixture of people for the problem at hand. I thank Professor Damodara Acharya, who actually is roping in stalwarts of this in their respective fields, like Professor Basu and others, in different areas. and it's very illuminating to all of us. We listen to top-notch experts in different directions. So we have a opportunity through this forum to listen to different forum experts and different areas. Thank you, sir, for initiating and spearheading this event. I thank Professor, our Honorable Vice Chancellor, Professor Ashok Mahapatra, who had very briefly highlighted the achievements of our university, the current status of the university. Professor Basu was, Professor Sudha Basu was not present today, could not be present today about IMMT. Professor Renu Sharma, who is with his team coordinating the events very successfully. I thank Dr. Renu Sharma's entire team. Thank Professor Bhavani Sinha for introducing Professor Basu, who is his teacher. It's quite gratifying to learn that Professor Sinha was under tutelage of Professor Basu. It's a great kind of the synergy observed in this forum. And I thank all our distinguished, I think, participants like INE members, faculty members of SOA, students of SOA who participated in this great event. And I think witness the kind of the lucid presentation of a great teacher like Professor P.K. Basu. Thank you, everybody. Good day, good night, and see you next lecture. Thank you, everybody.
Thank you. Excellent. It's nice. I mean, I feel privileged and honored to interact with all of you. It's a privilege to be here. It's a very...
Thank you.
Basu, may I take just 1 minute more?
Yes.
Sure.
Professor Basu, your lecture is actually recorded. Do you have the permission to circulate?
Oh, yes. It's a
Thank you
pleasure.
so much.
In fact, I expected that, well, I don't know, this title may be very bombastic, or I expected that students, more students should participate. And okay.
It's okay. Actually, they're all busy in their examination and other things.
Yeah, that's
you
good.
have participated.
I'll be happy to interact with them in future. It's no problem. I like this.
We'll really like you to be here physically with our students and faculty as when it actually permits. That will be our standing request. And another small thing is that we'll be sending by post a small memento that is courtesy of actually this university to you. Kindly receive it. Thank you so much. It was such a pleasure. And I must really thank Professor Sinha, who really introduced you to us, and we could really see you. I have heard your name earlier, but never had the opportunity to see you. Thank you so much.
Thank you.
So it was my pleasure, Professor Ajaj. I am unfortunate that at the last phase of Professor Basu's lecture, there was some internet problem and I was disconnected.
But anyway, the recorded thing will be available.
Okay.
Okay,
Thank you.
Okay, thank you, Prasantada. Thank you very much.
Okay. Good night. Have a nice time. Nice weekend.
Yeah. Also. Yeah.
Bye.
Thank you. Yeah. Bye.